So this is question number 16 from your CHMA11 2010 midterm, and the question is asking you to identify the one correct statement from these 5 statements. So that implies that 4 of these statements are going to be wrong. Now this question has been posed very conveniently because the last 4 happen to be those incorrect statements, and it's this first statement which happens to be correct. And so what I'm going to do in this video is focus just on this one statement, and you can take out your textbook and see why these other 4 statements are incorrect. So it says over here, a reaction rate cannot be calculated from the collision frequency alone. Now the collision frequency fluctuates depending on the temperature of the reaction. But what you need to know on a theoretical level is, if we were to draw this graph, and this happens to be an exothermic reaction, but an endothermic reaction will work fine. Right? The key point to keep in mind over here is that here you have reactants and you have your products. They turn into products as time proceeds. And this vertical axis is indicative of the energy of the molecules in the setup. And so what they're saying over here is that there's a difference between the energy level of the reactants and the products, and this change in energy, or this difference in energy, can be described by Gibbs free energy, sometimes as the delta H of the reaction. But this is a thermodynamic property, right? A thermodynamic property, and if you look at this question, it's really dealing with chemical kinetics, right? Not thermodynamics per se, but chemical kinetics. And this has to deal with the path to equilibrium. How do the reactants get to equilibrium? And one of the obstacles is the energy of activation, right? And the energy of activation, if you were to use the analogy of a hill or a mountain, is the energy required, or the height you have to reach before this reaction can proceed spontaneously, right? Afterwards, this reaction can proceed without any help. But it first must climb up this energy gap, right? And so this is captured by the energy of activation. And this has to deal with the reaction rates, and there's an equation for that, which I'm not going to use at this point. But the key point to keep in mind in this question is the collision frequency, right? The speed at which molecules are colliding in a reaction has a lot to do with the temperature, right? Which is also related in some ways to the amount of kinetic energy of each molecule. Right? And that can fluctuate as the temperature changes. As the temperature increases, the kinetic energy increases, and so the collision frequency increases, right? But so long as that kinetic energy is sufficient to meet this demand, this reaction will proceed. And if it's insufficient, it won't proceed. And so the reaction rate's not dependent on temperature alone. Without the energy of activation, you cannot determine the reaction rate. And there's an equation that describes this. And this would be the Arrhenius equation, where the rate of the reaction is equal to some constant multiplied by e to the power of negative, this is the activation energy, divided by, this is the gas constant, and this is the temperature, so this whole value, right? And from this equation alone, you can see how temperature is a factor, right? The gas constant is a constant. It's not going to be fluctuating. Right? This is also a constant, but this is your other variable, right? The activation energy. And so while temperature can be captured in some ways by the collision frequency, you also need to know the energy of activation. And so with the collision frequency alone, you cannot calculate K. And that is why A is correct. So this is question number 18 from your 2010 CHMA11 midterm, and the question reads as follows. For a reaction with a second order constant, which is the correct unit? So let's write out the rate of the reaction. The rate of a second order reaction, so rate or reaction rate, this is always going to be in molars per second. So how does the concentration change? Does it increase or decrease with respect to time? Is equal to some constant, right? And the constant has units, times, let's say we have A and B, right? For a reaction where A plus B goes to C. Another case of a second order reaction is, let's say B is exactly the same thing as A. So A plus A goes to C. And this would mean that the rate of the reaction would be K A times A, which would amount to K A squared. And these are the two common possibilities that you might see. In any case, they want you to know the constant, the units of the constant, right, of this value. And so let's rearrange this reaction, right, this expression, so that K comes onto one side, and you have K is equal to the rate of the reaction divided by, let's take this case because this subsumes the second case. And all of these are concentrations. It's a concentration of A times the concentration of B. And so let's start plugging in the units. So we said this is molars per second. This is molars. And this is also molars. And so you can see how what we're left with is the following units, right? Seconds to the power of -1 and molars to the power of -1. Now seconds is under the category of times, right? So this is just one of the metric units used to describe time. And so the response we see over here, molars to the power of -1 and times to the power of -1, is response C. So this is question number 20 from the CHMA11 2010 midterm, and the question goes as follows. Which of the following lowers the activation energy of a reaction? And so let's draw this diagram here to highlight what's going on. And so if the vertical axis is indicative of the energy and the horizontal axis of time, and this is a graph for the energy state of the reactants vis-a-vis the products. Let's say you have something like this. Then the energy of activation is that gap between what the reactants start off with and the highest state of energy that the reactants reach in this experiment, right? In this reaction, right? And this is the energy of activation. And so if you employ the analogy of climbing a hill, this is the highest point at which the reactants reach before they can slide down the hill, right, and become products. Now, as you could imagine, that this endeavor to climb a mountain or a hill comes down to how high the activation energy is. The energy of activation, if it's going to be really high, it'll be very hard for the reactants to reach this height. And so one thing a catalyst does is it brings it down. So it doesn't affect the difference between the energy state of the reactants vis-a-vis the products, but the path whereby the reactants can become products is altered. So let's take a look at what a catalyst might do to the energy of activation. So it provides an alternate path that ends in the same way, but by splitting this hill into two, you might say, it lowers the energy of activation. So you have these two little hills now, right? What you have is this, and you have another hill to climb. But neither one, these do not take on a cumulative value. neither one is as high, as high in altitude as the initial energy of activation. And so yes, adding a catalyst does lower the activation energy.